Hi everyone, in this video we'll solve example 3.2 from the book Applied Thermodynamics Mecon Kenti Disturb from chapter 3. Example 2, here the statement: steam at 7 bar and run is fraction 0.9 expand in a cylinder behind a piston isothermally and reversibly to a pressure of 1.5 bar. Calculate the change of internal energy and the change of enthalpy per kg of steam. The heat supplied during the process is found to be 547 kilojoule per kg. Calculate the work done per kilogram of steam. So this is, let's say, a cylinder. Inside it there is a piston. There is a steam inside this cylinder. Behind this piston there is expansion taken place. This cylinder moves from top dead center to bottom dead center, and expansion of the steam is taken place. The steam that is initially in the wet regions because there is dryness fraction 0.9. So let's come towards the statement that what kinds of data it has provided. Pressure P1, it is 7 bar, dryness fraction, that is 0.9. It said a cylinder behind a pistons expand reversibly isothermally. So it's isothermal expansion. Then T1 temperatures, initial state temperatures and final state temperature must be same. The final state pressures is P2 and it is 1.5 bar. In other words, we can also write P1 in terms of Newton per meter square, that is 7 multiplied 10 to the power 5 Newton per meter square. Similarly, 1.5 bar multiplied 10 to the power 5 Newton per meter square. Also, it says that the heat is supplied to be of 547 kilojoule per kg. What are our requirements? That is to find the change in internal energy and change in enthalpy. So from initial state, the steam is in the wet region and its dryness fraction is also given x1, that is 0.9. so at this pressure 7 bar, you can see from the associated steam table the UF1 value and UG1 value, and similarly the HF1 and HFG1 value. So I am writing the initial state corresponding enthalpies and internal energy values. At the initial state, U1 is equal to 1 minus x UF1 plus x UG1. Similarly, enthalpy H1 is equal to HF plus x into HFG1. Put the corresponding values in these two equations in order to get the internal energies and enthalpy at the initial state. After solving this on calculators, you will get the internal energy U1 value, and it is 2385.3 kilojoule per kg, and the enthalpy H1 value is 2557.3 kilojoule per kg. Also from this saturated water steam table, you can see at 7 bar the corresponding saturated temperatures Ts, that is equal to T1 and it is 165 centigrade, and is also equal to T2 because the process is isothermal as it is mentioned in the statement. Now the final state value we will see from the superheated region. The final state value we will see from the superheated regions at a temperatures of 165 centigrade and pressures that is given, it is 1.5 bar. So let me take the portion of the superheated steam table. So here I have taken the portion of the superheated steam table, that is our understudy. If you see that the temperature is 165 centigrade and the pressure 1.5 bar, the corresponding temperatures 165 centigrade is not available in the superheated steam table, but it is lie in the between 150 and 200 centigrade. So we will perform interplotting. Before moving forward toward the interplotting formula, you must familiar with some terms that is very important in interplotting. This is, let's say, T lower value, this is, let's say, T upper value, and in between, at which we are finding the corresponding internal energy and enthalpy, it is TA value. Let's say this is U lower value and this is U upper value. Lower value means that at a lower temperature 150 centigrade, upper means that the value of internal energy at a higher temperature 200 centigrade. Similarly, this is H lower value and this is H upper value. So you will just pick the values and you will put that in the interplotting formula. You will get the corresponding internal energy at a final state and enthalpy. So here I am writing the formula directly. Now put the corresponding values from this superheated steam table, enters in the center plotting formula, and you will get the final state internal energy. So so after simplification of these two, it is 15 by 50. After solving this, you will get the final value of U2 and it is 2603 kilojoule per kg almost. Now similarly, the final enthalpy, so after solving this, you will get the approximate value of the final enthalpy and it is 2803 kilojoule per kg. Now you are interested to find the gain in internal energy and it is equal to U2 minus U1. That is U2, that is 2603 kilojoule per. After solving this, you will get the gain in internal energy 217.5 kilojoule per kg. Now enthalpy change, that is H2 minus H1. (245.7 kilojoule per kg). This was our first requirement answer. This was our second. Next is to find the work output by the steam. We know that Q plus W is equal to change in internal energy. Then work done by the steam will be equal to change in internal energy minus heat supplied. Change in internal energy is 217.5 minus heat that is supplied, and it was 547. Solving this, you will get the work output by the steam. It is minus 329.5 kilojoule per kg. This negative sign means that work is done by the steam. Now let me draw its PV diagram. Initially the steam were in dry saturated. Initially the steam were in the wet region. Then expansion taken place at a constant temperatures and then reaches to its final state. So here the specific volume is V2 and here the specific volume is V1, and this expansion taken place at a constant temperature. Here the pressure is P1 and here the pressure is P2. The P1 pressure is 7 bar, 7 multiplied 10 to the power. This shaded area represents the work done by the steam. I hope you understand. If you still have any confusion, I hope you understand. If still there is any confusion, you can ask in the comment section. Thank you so much.